Welcome back to our video module on quantum mechanics. Thus far in our exploration of potential energy profiles, we've looked at the infinite square well and found solutions to the Schrödinger equation for multiple energies. We've looked at the simple harmonic oscillator and observed Gaussian waveforms for that potential profile. And most recently, we've looked at the free particle, where we have a continuous energy distribution in a negligible potential energy. Today, I'd like to take a look at a delta function potential profile where the delta function is a well. And in this energy arrangement, I'm wondering, what does the wave function look like? How do we work with the Schrödinger equation to find solutions? In this video, we'll take a first look at the delta well potential and identify the form of the solutions for the wave equation. Now, to start us off, I've written the time-independent Schrödinger equation for this potential profile in the yellow box. We can basically separate our potential profile into three areas. To the left and to the right of the delta function, we have areas 1 and 2. And at the location of the delta function, we'll have area 3. Now let's first take a look at areas 1 and 2. This isn't unlike the free particle solutions, except in the free particle solutions, we had the energy greater than the potential. But in this case, we're going to give the energy of the wave an energy less than the potential in that region. And we'll remember that in regions 1 and 2, the delta function is going to be 0. And to simplify our calculations, we're going to make a substitution that says k equals the square root of negative 2 me over h bar. And the intent of this substitution is pretty clear when we isolate the second derivative with respect to x, yielding the result the second derivative equals chi squared psi. And this is one of those cases where the Schrödinger's equation really shows its potency in that we've already identified the form of the solution that we need in regions 1 and 2. And while we could write down the general form of the solution as e to the negative kx plus b e to the kx, we can tell by simple evaluation that this is going to be an even function about the location of the delta function. So we can say psi of x equals a e to the negative k times the absolute value of x. And the reason we've chosen the negative is we're remembering that we have to have a normalizable solution. So anything that blows up as x becomes large is not a solution. Great, so with some quick math, we know the basic form of the wave equation in regions 1 and 2, and a quick sketch of an even function that's a decaying exponential yields us a wave function that looks something like this. So in summary, by simply starting with our Schrödinger's equation, identifying the relative location of E, mainly that it's negative, we're able to identify a form of solution that looks like this. And hopefully at this point, a couple things plague your mind. How do we get A? What is K? And what happened to the delta function? We haven't even looked at it yet. Join us in our next video as we use some really slick math to identify our K and use our normalization guidelines to identify our A. I look forward to seeing you then.